Hi, let's round up this introduction to the course with a little bit of material on graphics technology, how engineers communicate, and the evolution of this very venerable area of engineering graphics. So engineers, of course, communicate through many different channels, anywhere from plain language to mathematical formulas to quantitative data, so numerical data. Numerical data sometimes likes to be expressed in two-dimensional format, so we certainly communicate through charts, both two-dimensional, even three-dimensional. We also communicate through prototypes. Okay, we communicate with things that we can touch and feel, and that's oftentimes the best access to understanding how something works. And then, of course, we are very prone to communicating in a graphical manner, and the simplest most primordial expression of that, would be freehand sketching, which is an important competency and one that we will be covering in this class. Okay. Now, of interest is the matter of, or the subject of engineering graphics, because it's been known over time, and that has to do with the creation of formal engineering drawings. And you see there are pictorials on the left. Actually, the pictorial is not a formal engineering drawing, but it's certainly an important part of the tool set of graphics, for an engineer, and then more formal engineering drawings, orthographic views, sectional views, things like this, as depicted there on the right hand side. Okay, so of course graphics has been around for a long time. For as long as we've wanted to communicate in history in an engineering context, there has been graphics. Some of the earliest expressions of graphical engineering work, date back, to millennia before Common Era. As you see there, the Fortress is one example that's been identified. Of course, engineering really began with civil works primarily. So we're talking about buildings, roads, that type of thing. Roman Empire. You can think even before then, the pyramids in Egypt, etc. And then. When we get to the Renaissance, okay, so advancing really just 400 years, ago, we see a fundamental shift, and that fundamental shift is, of course, brought about by the scientific method. Okay, so the scientific method eventually leads to the Industrial Revolution. Okay, and that matters in a very particular way, and I'll get into that here quickly. Now, as we see the introduction of the scientific method, we start to be able to use graphics as a means of mathematical calculation, which is rather interesting in itself. Okay, so now we can calculate lengths and areas and volumes through graphical techniques as opposed to through numerical techniques. And the highest expression of that is really what's known as descriptive geometry, and you see some examples of that on the screen. Okay. Now, if you think in terms of how we've come to be to where we are today and the use of graphics today, you need to understand that we've transitioned as a result of the scientific method and then eventually the Industrial Revolution from a means of production that is artisanal in nature, okay, to one that is mass production in nature. Okay, and the thing about being an artisan producer, an artisan engineer, is that the designer and the maker live in the same body. They're the same person, or at the very minimum, they're very close to one another. So that lessens the need for formal communications between the designer and the fabricator. Not so today. If you consider the paradigm of mass production, it may very well be that the designer never even meets the maker. Okay, the designer and the maker may not even live in the same continent. There's a need, however, for total part interchangeability. If you're living in a mass production world, you take your car for an oil change, you expect that oil filter, to not have to be modified to the particular shape of your engine block or receptacle in any event. Okay, you expect those parts to be interchangeable. Well, that requires a very high definition as to how the part is to be made. Okay. We live, of course, in a world of not just national but transnational global supply chains. So again, speaking to the fact that the designer and the supplier may be in entirely different worlds. Okay, so that elevates, the need and the importance of proper communication and proper information in the graphical sense. Okay, even to the extent that an engineering drawing package, is in fact a legal document today, and it matters that who's right and who's wrong if there's a discrepancy between the designer's intent and the fabricator's production. Okay, one of our best tools against miscommunication in the graphical world is the use of standards. Okay, and that's something that will be very relevant, important here in the course. We will be following ASME/ANSI Y14 standards, specifically Y14.5. That's one of the biggies there, and then there's another one, Y1441, that deals with a so-called model-based definition. And no, of course, ANSI, ASME are not the only ones. Those dominate here in the United States. Of course, they are also in wide acceptance in other parts of the world, but other parts of the world also have other standards, that are both transnational in nature, such as ISO, and national in nature, such as Japanese standards, British, Russian, etc., etc. In every case, the intent in there is to provide an ambiguous interpretation of a drawing, common symbology, common rules, and create a shared acceptance across the engineering community. Now, let me say a few things very briefly about engineering technology, and I thought it would be well to begin with this picture that I took not very long ago here in the hallways of the University of Texas at Arlington. And what you see there is an old drafting table. And if you look a little closer in there, it's a surplus on it. It's on its way out. As is apparently an old CRT, an old cathode ray tube monitor, and another relic of our technical past. Well, before it got to this point, engineering graphics was in fact a mainstay of engineering education. And you did engineering graphics, and you learned them through what's used to be known as board drawing. And there you see some typical drafting boards, typical instrumentation that you would need, all manners of pencils and different hardness of the leads and softness of the leads, and erasers, even electrical erasers, eraser shields, triangles, scales, French curves, different templates of different kinds for circles, for ellipses, even for lettering. Very, very interesting. That used to be one of the things that you needed to do, be a good letterer. Okay, and these pictures here show what engineering graphics really used to be like. Most engineering companies would have a room that was dedicated to drafting boards, with the attendant staff, and also machines that would reproduce the drawings, from an original. Okay, now here's my set, from back in my youth, and you see there my compass set to the right. You see an eraser shield, rather important actually, if you didn't want to mess up other lines in your drawing, if you just had a small mistake somewhere. On the lower left in there, you see a piece of cloth, and the reason I needed that is because a lot of my drawings had to be done in ink, so I would do them first in pencil and then in ink. And then I have a couple of implements in there. That's actually a matchbox, and I didn't need the matches, but I did need the striker for the matches in there in order to sharpen my lead for my pencil. And then perhaps the most interesting item in there would be the razor in there, and the razor was to make corrections to the ink drawings once they were dry. And ink was, as I say, not a requirement for every drawing, but I did have to use it regularly, and that was the device there that you see on the screen that I had to actually put in a few drops of ink and regulate the width of the line by turning a little screw knob in there. Okay, there are my triangles. For me, high technology was using that Rotring 2000 equipment. So those were actually ink pens. They already had the proper width. So I didn't have to worry about adjusting the width or the thickness of the line, nor having any ink drop and ruin my drawing, which would happen on occasion. Right. Here's an example of the lettering. That every engineer had to learn how to do. And I'll just walk you here through some examples, things that I had to do when I was back in my early years. That's an example there on the screen of an exercise in descriptive geometry, and generating the true view out of two oblique views of a surface. Okay, some of my ink drawings, you see there are some examples of, let's see, what do we have? Involutes, I guess, cardioids, spirals. Here's a hypocycloid, okay, and you can see there are some errors, even some indications there from my professor. Okay, geometrical construction was an important thing to learn. How to create, for instance, three circles that would be tangent to one another contained within a triangle. So that's what you see there on the drawing to the left on the upper right hand quadrant. Also drawing tangent circles to two circles. Any number of geometrical constructions that turned out to be very useful if you knew how to create them with a ruler and a compass. Okay, these are examples of pictorials. So these are 3D looking representations of a part, and then down in the bottom you would see what's known as orthogonal projections, or front, top, side views of the same parts. Okay. Those come in different varieties. We'll get into that later in the course. We'll learn what all those are and learn how to do them only at a sketching level, of course, not at the level of precision that I was required to do. Here are some perspective drawings. This is more of within the architectural realm, but useful on occasion if you have some pictorial and you want to add flair to it. You might resort to perspective. Okay, and there's another example, and then finally, all that capability was so that you would be able eventually and ultimately to create engineering drawings, which will generally consist of multiple orthographic views, two-dimensional views, and then an isometric or axonometric view there where you can understand what the part looks like in 3 dimensions. Okay, and some additional examples there yet. Now, of course, the world has changed quite a bit with the introduction of the computer, and that began with 2D drafting. Okay, so this was our first walk, if you will, in the long walk from board drawings to what we have today. Was the introduction of the 2D electronic canvas. Now, in 2D, really, you were just doing the same lines and circles and arcs that you would do by hand, but now, of course, you'd be able to do them with a computer with all the advantages thereof. Okay. Eventually, we moved into 3-dimensional drawings, but this didn't happen instantaneously. We first transitioned through something known as wireframe. Okay, obviously 3-dimensional computer representations are very computing intensive, rather CPU intensive, so they weren't available at the beginning. In fact, one of the coolest things to come in the market, were these computers. That particular one is from a company no longer exists, Silicon Graphics. In there, and boy, if you had a Silicon Graphics workstation, you were really at the top of the food chain. And around that time is when, and this, by the way, was all Unix based. None of this was available for Windows. The Windows computers simply didn't have the horsepower to run this software. But that was the first time that you could see actual fully rendered 3D drawings. And then finally, that software transitioned into the analytical realm. So now you could have 3-dimensional bodies and do analysis. And at the beginning, interestingly enough, the CAD and the analysis were 2 separate packages. But over time, those merged together. And this is something that we alluded to in the previous video. So again, just a quick whirlwind tour of this technology. If nothing else, you should consider yourself lucky that you are where you are, because you no longer have to worry about the artistry of engineering graphics. You have to learn how to use the tools, granted, but then you're free to design. You're free to concentrate on what really matters, which is to make great inventions, and the computer will support all that and give you tremendous capability both to visualize and to analyze and to communicate your designs, and that's where the gold is.